Welcome to DAR Tutors for online and home tuition. In this video, we will explore key concepts in bivariate statistics, a fundamental topic within the IB mathematics, applications and interpretation higher-level curriculum. By the end of this session, you will be able to, first, analyze the relationship between two numerical variables using scatter diagrams. Second, calculate and interpret Pearson's product moment correlation coefficient, R. Third, understand and interpret the coefficient of determination, R squared. And finally, use a line of best fit to make and evaluate predictions. Let's begin by introducing bivariate data. Bivariate data means we have two variables recorded for each individual. Our goal is to find a model that best fits this data and measure how strong the relationship between these variables is. For example, in a junior discus tournament, we might record each athlete's age and the distance they throw. Here we see data for 12 athletes. For athlete A, we have an age of 12 years and a throw of 20 meters. This pairing of data points is what we call bivariate data. A key step is identifying the variables. The independent or explanatory variable is the one we expect to influence the other. The dependent or response variable is the one that is affected. In our discus example, it's reasonable to expect that the distance thrown depends on the athlete's age. Therefore, age is the independent variable, and the distance thrown is the dependent variable. A change in age explains a change in the distance thrown. The best way to visualize the relationship between two numerical variables is with a scatter diagram. A scatter diagram plots each pair of data as a point. We always put the independent variable on the horizontal axis and the dependent variable on the vertical axis. By looking at the pattern of these points, we can begin to understand the relationship between the two variables. We can analyze scatter diagrams based on three main characteristics: direction, linearity, and strength. Understanding these helps us describe the correlation. The direction of the scatter diagram tells us the sign of the correlation. If the points generally go upwards from left to right, we have a positive correlation. This means that as the independent variable increases, the dependent variable also increases. If the points go downwards, we have a negative correlation. As the independent variable increases, the dependent variable decreases. Next is linearity. This describes the shape of the relationship. If the points cluster along a straight line, the relationship is linear. The correlation we are studying is linear correlation. If the points follow a curve like this, the relationship is nonlinear. In this chapter, our primary focus is on linear correlation, which forms the basis for the calculations we will perform. Finally, strength indicates how closely the points fit this linear pattern. If the points are tightly clustered around a line, the correlation is strong. If they are more spread out, the correlation is moderate. If they are very scattered, it is weak. A very strong correlation suggests a reliable relationship between the variables, while a weak correlation suggests a less predictable one. Another important feature to look for are outliers. An outlier is an isolated data point that falls outside the general trend of the data. Here, this point is an outlier because it deviates significantly from the pattern of the other points. An outlier can be the result of an error or a genuine unusual observation. Outliers can have a substantial impact on our analysis, so it's essential to identify and consider them carefully. A high correlation between two variables does not automatically imply that one causes the other. Correlation only describes the direction and strength of the relationship. It does not explain why that relationship exists. Here's a common trap: finding a strong statistical link and mistakenly concluding a causal link. Consider this. Studies have shown a strong positive correlation between the number of firefighters at a fire and the amount of damage the fire causes. Does this mean more firefighters cause more damage? No, of course not. The true cause is the size and severity of the fire. Both the number of firefighters and the amount of damage are effects of this third variable. Another fascinating example. The number of television sets sold in London was found to be strongly correlated with the number of stray dogs collected in Boston over several years. This is clearly a coincidence. There's no causal link whatsoever. It's crucial to evaluate these relationships with critical thinking, not just raw numbers. A causal relationship exists only if a change in one variable, the explanatory variable, causes a change in the other, the response variable. always consider other potential factors, known as confounding variables, that might be driving the observed correlation. Our visual assessment of scatter diagrams is subjective. To get a precise objective measure of linear correlation, we use a formula. This brings us to Pearson's product moment correlation coefficient, denoted by the letter R. This value provides a statistical measure of the strength and direction of the linear relationship between two variables. The formula for R is given by R equals the sum of the product of the deviations of x and y from their respective means, all divided by the product of their standard deviations, which are represented in the denominator. You are not required to memorize or calculate this by hand for the IB exam. Instead, you'll use your graphics display calculator. So how do we interpret the value of R? First, the value of R always falls between 1 and plus 1. Second, the sign of R tells us the direction. A positive R means a positive correlation. A negative R means a negative correlation. If R is exactly 0, there is no linear correlation. Third, the size of R tells us the strength. A value close to plus 1 or P1, like 0.9 or 0.8, indicates a strong correlation. A value close to 0, like 0.1 or 0.2, indicates a weak correlation. Remember, R only measures the strength of the linear relationship, not a curved one. While Pearson's R is a continuous scale, we often need to describe the strength of a correlation in words. This table provides a useful guide. A perfect correlation has an R value of exactly 1 or 1. This occurs when all the data points lie on a perfectly straight line. As the points spread out from a perfect line, the correlation becomes weaker. The closer R is to 0, the weaker the linear relationship. For instance, an R of 0.9 suggests a very strong positive linear correlation, while an R of 0.6 suggests a weak negative linear correlation. This guide helps translate a calculated R value into a meaningful description of the data's pattern. Let's work through an example to see how to calculate and interpret Pearson's R using a graphics display calculator. The botanical gardens are testing a new chemical to control a beetle infestation. They have recorded the quantity of chemical used and the number of surviving beetles. Here is our data. 5 samples. The quantity of chemical is our independent variable, X, and the number of surviving beetles is our dependent variable, Y. Our task is to determine the correlation coefficient. The first step is to input this data into your calculator. Open the statistics mode, find your list editor, and enter the X values into one list, say L1, and the Y values into another, L2. Once the data is entered, you need to find the linear regression function. This is typically in a KLC menu. Select lin_reg x plus b or something similar. Make sure to specify your X and Y lists correctly. The calculator output will show several values, including the coefficient A, the y-intercept b, and importantly, R. Here, R is approximately 0.859. The calculator also gives us R squared, which we'll discuss next. Now, let's interpret this result. The value R equals 0.859 is negative, which tells us the correlation is negative. The absolute value is 0.859. If we refer to our guide, this falls into the strong negative category, as it is between 0.95 and 0.87. So, we describe the correlation as a strong negative correlation. But what does strong negative correlation mean in context? It means that as the quantity of chemical used increases, the number of surviving beetles tends to decrease. The strength of this relationship is strong, suggesting that the chemical is effective. To help describe the correlation between two variables, especially in terms of how much one variable's variation explains another's, we use the coefficient of determination, R squared. The coefficient of determination is simply the square of Pearson's correlation coefficient, R. So if you know R, you can find R squared by squaring it. Conversely, if you know R squared, you can find R by taking the square root, remembering that R can be negative. So R squared equals R squared. The beauty of R squared lies in its interpretation. When a causal relationship can be assumed or is highly plausible, R squared represents the proportion of the variation in the dependent variable that can be explained by the independent variable. In other words, it tells us what percentage of the changes in y are accounted for by the changes in x. The remaining percentage, 1 minus R squared, is the variation that is due to other factors or random chance. For example, in our beetle chemical experiment where R was approximately 0.859, squared is 0.859 squared, which is approximately 0.738 or 73.8%. This means that 73.8% of the variation in the number of surviving beetles can be explained by the variation in the quantity of chemical used. The remaining 26.2% is due to other factors, such as environmental conditions or beetle immunity. With a sufficiently strong linear correlation, we can draw a line of best fit to model the relationship and make predictions. For HL students, a line of best fit by eye is a key skill. There are 3 steps to drawing a good line of best fit by eye. Let's use our discus tournament data as an example. The mean age is 15 years, and the mean distance is 29 meters. First, calculate the mean of all the x values and the mean of all the y values. We call this the mean point. Second, plot this mean point on your scatter diagram. Every line of best fit must pass through this mean point. Third, draw a line through the mean point that follows the general trend of the data. You should aim to have roughly the same number of data points above the line as below it. Here's the scatter diagram for the discus data with our mean point, 1529, marked. A line has been drawn through it, with points spread fairly evenly above and below. This line is our line of best fit by eye. We can use our line of best fit to predict values for the dependent variable. There are 2 types of predictions we can make: interpolation and extrapolation. Interpolation is when we predict a y value for an x value that is between the lowest and highest x values in our original data set. This is generally considered a reliable prediction because we are within the observed range. Extrapolation is when we predict a y value for an x value that is outside the range of our data. For example, in our discus data, we don't have athletes younger than 10 or older than 20. Predicting for these ages would be extrapolation. Extrapolation is often unreliable because it assumes the linear trend continues indefinitely, which is rarely true in real-world scenarios. Let's apply this to our discus data. The range of ages in our data is from 10 to 20 years. We can use the line of best fit to predict the distance an athlete might throw at age 14. This is an interpolation. We find 14 on the age axis, go up to our line of best fit, and then go across to the distance axis. This gives us a prediction of approximately 26 meters. However, let's consider extrapolating. If we use this same line of best fit to predict for a 50-year-old, the model predicts they would throw 144 meters, which is almost double the current world record. This is a clear indication of an unreliable extrapolation. Always be cautious when predicting outside your data range. We have now covered the main theoretical components of bivariate statistics. Let's practice with some IB-style questions. At the 10-minute mark of this video, I want to pause for a moment. This content, and much more, is covered in detail at DAR Tutors. If you are struggling with your IB, A-level, or IGCSE curriculum, or simply want to achieve your highest potential, I encourage you to contact DAR Tutors for expert tuition. Our tutors are dedicated to your success. Now let's get back to our practice problems. We will solve 5 questions that test our understanding of correlation, coefficient of determination, and line of best fit. The full worked solutions will be provided. Here is our first practice question. A health researcher notices that the incidence of multiple sclerosis is higher in some parts of the world. They recorded the latitude and incidence of MS for 20 countries. You are given the R value for the association and a scatter diagram. Your task is to describe the correlation and interpret its implications. Take a moment to read the question and think about how you would solve it. Now let's look at the solution. For part A, we are given RHD 0.887. This is a positive value, so the direction is positive. The magnitude, 0.887, falls between 0.87 and 0.95, which means the strength is strong. Therefore, we describe the correlation as a strong positive linear correlation. For part B, a positive correlation means that as latitude increases, MS incidence also tends to increase. Higher latitudes are found near the Earth's poles, while lower latitudes are near the equator. Therefore, a strong positive correlation implies that the incidence of multiple sclerosis is higher near the poles. Question 2 asks about the coefficient of determination. Again, pause the video and work out your answer. Let's review the solution. For part A, to find the coefficient of determination, we simply square the correlation coefficient. So r squared is approximately 0.429. For part B, we interpret this value. Since screen time is our independent variable, we can say that 42.9% of the variation in students' academic performance can be explained by the variation in their screen time. This implies that the other 57.1% of the variation in academic performance is due to other factors, such as study habits, quality of teaching, or natural ability. Our third question involves a line of best fit and the concept of extrapolation. Here's the solution. For part A, we plot the points on a scatter diagram. For part B, we first find the mean point. The mean weight is 13 kgs, and the mean speed is 7.83 meters per second. We plot this point, then draw our line of best fit through it. For part C, we use our line to predict the speed for an animal weighing 25 kilograms. This is an extrapolation, as our data only goes up to 20 kilograms. We find the prediction is approximately 1 meter per second. For part D, we must comment on reliability. Since 25 kilograms is outside our data's range of 5 to 20 kilograms, this is an extrapolation. The linear model might not hold true at much heavier weights, as a real animal's speed would likely reach 0 before its weight became impossibly large. Therefore, our prediction is unreliable. Question 4 asks us to find a correlation coefficient from a given r squared. Let's work through the solution. For part A, we use the relationship r squared equals r squared. To find r, we take the square root of r squared. So r is the square root of 0.729, which gives us approximately 0.854. Notice here that because the context is tree growth, we assume a positive correlation, as trees tend to grow larger with age. If there was no contextual information, we would typically give both the positive and negative roots. Now for part B. Assuming a positive correlation, as is reasonable for age and trunk size, an R value of 0.854 is very close to 1. In our guide, 0.854 is between 0.7 and 0.87, which is described as moderate. We can therefore conclude this is a moderate to strong positive correlation. Our final question is about causality and confounding variables. Pause and consider this classic example. Let's discuss the solution. Part A is a direct test of your understanding of the correlation versus causation principle. While it may seem like there's a connection, eating ice cream doesn't cause people to drown, and drowning doesn't make people crave ice cream. The correlation is coincidental. Correlation only shows that two variables move in a similar way. It does not explain the reason. So, what could be causing both variables to increase? For part B, we need a third confounding variable. The most obvious answer is temperature. On a hot summer day, more people will go to the beach and swim, increasing the risk of drowning. At the same time, more people will buy and eat ice cream to cool down. Therefore, temperature is the underlying cause for both variables' increases, creating the illusion of a direct correlation between ice cream and drowning. Let's quickly recap what we've covered today. We learned that bivariate data involves two variables. Scatter diagrams allow us to visualize the association, looking at direction, linearity, strength, and outliers. Pearson's R gives a precise quantitative measure of the strength and direction of linear correlation, while r squared tells us how much variation in one variable can be explained by the other. Finally, We saw that a line of best fit can be used to make predictions, but we must be cautious when extrapolating outside the data range. Remember the crucial distinction between correlation and causation. You should now be able to apply these concepts to various datasets and interpret your findings, which is a key skill for the IBAIHL exam. Thank you for watching. For more detailed explanations, one-on-one support, and expert guidance for your IB, A-Level, or IGCSE studies, please do not hesitate to contact us. Dart Tutors is here to help you succeed.